So last session we had ended with this thing. See parasitics. We have started with capacitive parasitics. So we considered a section channel MOSFET. So drain source gate, and there is p-type substrate, that is a bulk terminal denoted as B, and we have taken a cross-sectional view of the drain region, and we have written here that because there is a p-type substrate in connection with n plus drain, that is heavily doped, um, what to say, pentavalent impurity. So we see here that there is a heavily doped drain n plus, and because there is a p-type substrate below that, there is a depletion region formed. So there are two depletion layers which are shown. The green colored depletion layer, it represents the zero bias depletion, that is when no potential is applied at the drain with respect to the source. I repeat, zero bias depletion refers to the depletion layer formed when VDS is equal to 0, and as soon as some potentials are applied between drain and source, then the depletion layer will shift. So the red color depletion layer is called as non-zero bias depletion, and we have denoted two capacitances, CSW, that is side wall capacitance, and CBW, that is bottom wall capacitance, and we have denoted that both side wall and bottom wall capacitance are under the category of diffusion wire capacitance, right? So we can say here zero bias depletion fine. So I'm going to write down some semiconductor physics equations which you must have studied in your second year directly. So VR is the applied junction voltage, VBI is built-in potential, CJ0 is zero bias capacitance, which is nothing but Cj for Vr equal to 0. Okay, junction capacitance with no junction voltage applied. Okay, and we have Cj equal to Cj0 into 1 plus junction voltage upon built-in potential raised to minus 1 by 2. So let's say let this be equation number 1. Then we have the built-in potential VBI is equal to KT upon Q, natural logarithm of acceptor impurity concentration into donor impurity concentration upon intrinsic concentration square. Let this be equation number 2. Okay, and Cj0 is equal to okay. So the junction capacitance Cj consists of zero bias capacitance, and we have built-in potential, and we have in turn mathematically expressed VBI and Cg0. Okay, and again VBI applies here. Okay, so as you know, K is the Boltzmann constant. It's very clear. T is the temperature in Kelvin. Okay, so we can write equation number 1 shows that as the junction potential increases, Cj reduces. Okay, and so we can actually make a tabular form for different values of Vr. Okay, so I'll again write the equation number 1. So VR is equal to 0. The value of Cj is Cj0. So you can just put VR as 0 and you will get it 0. Now for VR is equal to VBI. So VR is equal to VBI, and we get Cj0 into 1 plus 1. So 2 raised to, so it will be 0.707. It will be 0.71 Cj0. If the value of VR is 2 times VBI, we get 0.58 times Cj0. It is 3 times built-in potential. We get 0.5 times 0 bias capacitance, and for 4 times VBI we get 0.45 times Cj0. Okay, so so 0.71, 0.58, 0.5, 0.45. 0 VBI, 2 VBI. Okay, so again we are coming to the same conclusion that as VR increases, Cj reduces. Okay, now we come to know. Now we come to what is called as a multi-layered capacitance model. So I'll directly paste the picture here. Okay, here. So this is it is called as multi-layered capacitance model because we are here trying to understand what are the capacitances involved when a wire or a communication medium is a sandwich between two layers on the silicon wafer. So we can see here that there are three wires which are running between two layers. I'll highlight them, you will come to know. Okay, so this is the first layer called as layer n plus 1, and there is a bottom layer called as layer n minus 1, and the wires are on layer n. Okay, so these are the wires. This is wire number 1, wire number 2, and wire number 3. So there are three wires W1, W2, W3 which are running parallel to each other, and they are assumed to be at layer n. There is one layer above these wires called as layer n plus 1, and there is one layer which is below called as layer n minus 1. And we can see that the distance between layer n and n plus 1, it is h2, right? So h2 is the distance between layer n plus 1 and n. Similarly, h1 is the spacing between layer n and layer n minus 1. Now the spacing between the wires, as mentioned before, is s, and the width of wire is w. Okay, and this is the thickness, right? So all three wires are having same dimensions. The spacing between the wires is s, the width of the wires is w, and all the wires are having same value of thickness t. So h2 spacing between n plus 1 and n, h1 is the spacing between layer n and n minus 1. Thickness of all the wires are having spacing s units between them, and the width of the wire is w. And we are seeing here the different capacitances which are involved. So okay, so we have the first capacitance CAT. So CAT is called as area capacitance. Hmm? And we have CAB here, another capacitance is there. So CAB is called as area capacitance bottom. Okay, so CAT is the area capacitance between the wire and the upper layer. Okay, and CAB is the capacitance between the wire at layer N and the layer N minus 1. So CAB, area capacitance bottom. There is something called as a coupling capacitance CC between two wires. We see here wire 1 and wire 2 are having a coupling capacitance CC. Similarly, wire 2 and wire 3 having another coupling capacitance here. So maybe I can write it like this: W1, W2 and W3, the three wires W1, W2, W3. Similarly, I have another capacitance CFT, which is here. It is the fringe capacitance with respect to the upper layer or the top layer. Similarly, I have CFB, that is a fringe capacitance bottom. So I repeat, CAT, that is this thing. CAT is the area capacitance with respect to the upper layer. CAB is the area capacitance with respect to the bottom layer. We have coupling capacitance is CC between two wires W1 and W2, W2 and W3. Similarly, we have another capacitance CFT, fringe capacitance with respect to the top layer, and we have CFB, fringe capacitance with respect to the bottom layer. Okay, so everything has been written here, so there is no ambiguity. Okay. Now there are some mathematical dependencies which have been established by researchers over time. So I'll just write them down. The capacitance CAT, that is area capacitance with respect to the top layer, is a function of the width of the wire and the vertical separation H2. Okay. The second dependency is the area capacitance with respect to bottom layer is similarly dependent on W and H1. Okay. The third dependency is for the coupling capacitance CC, which is a function of the distance of separation between the wires and the thickness. Okay. So we can name them equation 4, equation 5, equation 6. Okay. So from this equation we write that for coupling capacitance CC, as distance of separation reduces, CC will increase. Okay, it's very simple. So if I bring the two wires W2 and W3 closer to each other, then the coupling will increase. That is why I say that when S reduces, the coupling capacitance will increase. So I have written for coupling capacitance CC, as S reduces, CC will increase. Okay, and also it is found that as the thickness of the wires reduces, CC will reduce. Okay, so now we have two opposite relationships here. Okay, so I say that as S reduces, CC increases, as T reduces, CC reduces. So there is a direct proportionality between CC and T and an inverse proportionality between CC and S. So I can summarize this. I can say that the coupling capacitance is proportional to T upon S. Okay, but the fact is um, when technology is scaled down, that is W comma L of MOSFET reduces, the distance of separation S reduces faster than the reduction in T. Okay, so when technology is scaled down, that is WL are reduced, S reduces faster than reduction in T. Okay, so we can conclude that CC will increase. Okay, so as I said, okay, so now this is undesirable. We do not want the coupling capacitances to increase. It is undesirable effect. This is undesirable. Solution to the above problem is to use low K materials, that is having lower values of epsilon r, that is relative permittivity. So in the yesteryears, you know that C is equal to A epsilon upon D, which is equal to A into epsilon 0 epsilon r upon D. So here this epsilon r is known as relative permittivity. Okay, so air, silicon dioxide, silicon nitride Si3N4, silicon itself, hafnium oxide, and we have zirconium dioxide. Okay, and the values for air, it is 1, for SiO2 it is 3.9. Silicon nitride, it is 7.8. Silicon, it is 11.7. Hafnium, it is 20. And zirconium, it is 23. So here, in order to solve the problem of multi-layered capacitance, we have to use lower values of K, right? Not preferred. Okay. So this was about the capacitive parasitics, and now we go on to inductive parasitics. As I told you that inductive parasitics become more prominent, especially at higher frequencies, and the source of this inductive parasitics is actually the pins of the IC. Consider an off chip. Off chip means consider an off chip okay. So consider an off chip power supply driving a certain chip. Off chip means which is outside the chip. So this is my chip. LP represents the package inductance, and IC pin. We are assuming that this is a CMOS logic chip. Okay, and we discussed before that for CMOS logic, the output voltage is rail to rail. That means it goes from VDD to ground to VDD. This is called as fully restored output levels, also known as so here output voltage swing is VO max minus VO min is equal to VDD minus 0 equal to VDD volt. Okay, and if you want to find out what is the VL which is created across the package inductance LP, then we have VL equal to LP into DIS by dt. Okay, in steady state condition, L acts as short. Steady state means actually T tends to infinity. L acts as short circuit, because of which VL is actually 0. Okay, in steady state, that is T tend to infinity, L is acting as short circuit, so VL is equal to 0. So I can say this is static operation. For dynamic operation, assume the package inductance is equal to 0.5 nanohenries, and change in IS is 1 ampere per nanosecond. Okay, so we can say that which is equal to dis by dt. Okay, so dis by dt is equal to 1 ampere per nanosecond. Okay, so now we can calculate the value of VL. Thus VL is equal to LP into dis by dt, which is equal to 0.5 nanohenry into 1 ampere per nanoseconds. Upon 10 raised to minus 9 seconds. Okay, which is equal to 0.5 volts. Okay, so basically this calculation tells us that we got VL as 0.5 volts for 1 gigahertz frequency. Okay, so for deep sub micron VLSI technology, channel length L is less than 100 nanometers and the supply voltage VDD is less than 1.2 volts. Okay. Okay, for deep submicron technology, length is the same. So that means what? I have to replace this VDD from 5 volts to 1.2 volts. Okay. Okay. So out of this 1.2 volts, 0.5 volts is getting already dropped across the inductor, that is a parasitic inductance. So how much will go inside? There will be a logical error inside. Okay. So 0.5 volts out of 1.2 volts is getting dropped across so 42%. That's fine. So we discuss about the problem, then we have to discuss about solutions also. Okay, so thus we complete resistive, capacitive and inductive parasitics, and we move on to the next topic, it is pad design. And pad design will take time, so I'll just mention some of the packages which are used for VLSI ICs. What is the expansion of this abbreviation DIP? This is known. What does DIP stand for?
Dual inline package.
Okay. PLC stands for plastic leaded chip carrier. Then we have PG, it stands for pin grid array. Then we have PQFP, which is used in our Spartan 3 FPGA IC available in lab. So that actually stands for plastic quad flat pack. Then we have BGA, which stands for LGA, stands for land grid array. So the latest microprocessors from both Intel and AMD use this package land grid array, and this package has a capacity to hold more than 2000 pins in a quad format, that is 500 pins on one side of the IC. FFG. FFG is the latest package which is used by Xilinx as well as Intel for their latest FPGAs. So FFG is little complicated. It is a flip chip, fine pitch, MSI chips, medium scale integration, used for CPLDs. To 100 pins. So AMD's Ryzen 579 and i7 i9 from Intel, all of them use land grid array, and here Xilinx such as okay.